All right, welcome back to Loving the Physics, Mr. Goldthorpe. So now we're going to move on to the mathematical side of gravitation. And Isaac Newton made a big proposition. He proposed that the force of gravity should exist between any two masses, anywhere in the universe. And so we called this Newton's universal law of gravitation. And I'm going to show you the equation that he came up with. So on the left-hand side, let's draw a nice large mass. And we'll call this mass 1. And then we'll do a smaller mass over here. And we'll call that mass 2. Now what he's saying is that these two masses are going to exert a force of attraction on each other. So essentially, if one exerts a force on 2, a force of attraction, which he called Fg, if one exerts a force on 2, then based on Newton's third law, 2 will exert an equal but opposite force on M1. Even if they're of different masses, these forces will be equal but opposite. And he came up with an equation for this one that was actually kind of logical. I'll kind of build it with you here. So it starts out with this quantity Fg equal to. Now on the top part of this equation, it made sense to him that the bigger the masses, the bigger the force. So therefore it will have a direct relationship with both masses, M1, M2. But he also realized that the closer these masses are together, the stronger that force should be. So we introduced this letter R, and R will be the distance between these two masses, which I'll show you. And he said that it's going to be an inverse square relationship. And therefore, the smaller the R, the bigger the force. And so on the diagram, let me just show you what R specifically represents. It is a distance from center to center. Okay, that's the distance R that we're actually talking about here. The distance between the centers of these two masses. Good. And then there's a constant with this equation as well, which he called big G, the gravitational constant. So here's the equation for the force of gravity between any two masses. And I just want to make a note here underneath where G, the value for G, which is on the back of your formula sheet, by the way, is 6.67 times 10 to the negative 11. And the units are Newton meters squared per kilogram squared. And we can learn something kind of important about the units here. If you look at the units for big G, can you see therefore that the distance has to be in meters, the masses have to be in kilograms, and we're going to end up getting newtons as a result. Good? So this is the universal law of gravitation. Any two masses will attract each other based on this formula. Okay, let's try a couple of examples that relate to this formula. In the first one, we're going to have two objects that happen to have equal masses. And we want to figure out what their masses happen to be. Okay, so we start with his equation. So we have Fg equal to big G M1 M2 over R squared. But we're told that they're equal masses. So what we can do is we can let M1 be equal to M2 and let them both be equal to something called M. Now if you look at the formula here, that means we have M1 times M2, which becomes M times M. So what is M times M? And it will be M squared. So that's how we reduce this equation when they have equal masses. Now all we need to do is just solve for little m. So let's cross multiply. Fg R squared is G m squared divided by g. We end up getting m squared is equal to fg r squared over big G, and then we can square root that. All right, so we end up getting m equal to the square root of, so Fg. Now you realize Fg has to be in newtons. This one says 49.2 micronewtons, and that would be 49.2 times 10 to the negative 6 newtons. Make sure you use standard units. R, they are 17 centimeters apart. So please don't think that R happens to be radius, by the way. R is the distance from center to center. So that is the distance R, but make sure you convert it to meters. That'll be 0.17 meters, and don't forget to square that. And remember G, which is true for any location in the universe, is on the back of your formula sheet. It is 6.67, 10 to the negative 11. Okay. And that comes out to be about 146 kilograms for each of those two masses. Okay, so you can see it's reasonably straightforward here. You just have to remember if it's equal masses, it converts to m squared. And then we're good. All right, we have one more example. This one's a bit more interesting. And that is what happens if you have more than two masses. So for this one, I'm going to encourage you guys to have different colors. Let's take a look at the forces acting for each of the pairs of masses here. First of all, we have M1 and M2. Don't forget that they're always going to be attracting each other. So M1 is going to exert an attraction force on M2, pulling it towards M1. Think of it almost like tension force. It acts along the string away from the mass. But if one exerts a force on 2, 2 exerts an equal but opposite force on 1. So those forces are equal but opposite. But we don't really care about M1. We only care about M2. So let's label the one on M2. Let's call it Fg between, let's say, 2 and 1. I'm going to use two subscripts so I know which two masses I'm actually talking about. Okay, I'll change the color now. Let's now talk about 2 and 3. So we know that 2 is going to exert a force of attraction on 3. 3 exerts an equal but opposite force on 2. Again, we only care about 2, so that would be Fg 2, 3. Finally, with a new color, you can see that 1 and 3 will also attract each other. So 1 is going to exert a force of attraction on 3. 3 exerts an equal but opposite force on 1. But can you see that neither of these two forces acts on M2, so we don't care. All right, so now we actually have our formula, our force diagram, and that's how we start this question. Now the next steps are actually pretty logical. We need to figure out what these forces happen to be. So let's first find Fg21. This will be G M2 M1 over R, if you wish, 21 squared. Notice I'm trying to match the subscripts with the original two numbers. So this becomes 6.67, 10 to the negative 11. Mass 2 is 6,000. Mass 1 is 4,000. And the distance between 2 and 1 is 15 millimeters, which is 0.015 meters. And don't forget to square that. I'll calculate that soon. Let's just do the other one too. So Fg 23 becomes G M2 M3 over R 23 squared. So 6.67, 10 to the negative 11, M2 again was 6,000. M3 is 5,000. And the distance between 2 and 3 is 10 millimeters, 0.010. And then don't forget to square that. Okay, so let's just calculate both of these. Okay, so the first one's about 7.115 newtons. And the other was 20.01 newtons. Okay, so now we have the magnitudes for each. All right, let me just copy that force diagram here. Bring it down. Okay, so those are our two forces. And now we know the values for each of them. Let's now find the sum. So I'll do a different color here. So what I'm looking for here is the net Fg on 2, which technically speaking is Fg21 plus Fg23 as a vector sum. So you notice there's arrows on the top. Can you see this is one-dimensional? We'll need to have a reference system for this. Let's say we choose to the right is positive and to the left is negative. Okay, well what we'll see here, go back to green, Fg21 is going to the left. So that's going to be negative 7.115. And then Fg23 is positive, going to the right, 20.01. And how many sig digs do we get here? Looks like just 2 based on the distances. So that comes out to be 13 newtons, which is positive, which means it's to the right. Okay, so that's a net question. And again, the key for this one here is make sure you draw a proper force diagram, calculate the two forces, and then just use a reference system, because it's 1D, to figure out the net force. All right, before we finish this first part of the lesson, I thought I put one more on here that has no numbers, but just a strategy for how you'd find the net force on M2. I do recommend you try this yourself first. Pause, give it a try. Okay, so hopefully you've given it a shot. Let's take a look at it. So we're looking for the net force on M2. So again, M1 is going to exert a downward force on M2 of attraction, then 2 exerts an equal but opposite force on M1. And there's our, again, we care about M2, so that's your Fg21. Change the color. 2 and 3 are also going to attract each other. 2 exerts a force on 3. 3 exerts an equal but opposite force on 2. There's our Fg23. And if you're interested, 3 and 1 will also exert forces of attraction on each other, but neither of them are acting on M2, so we can ignore that. Now, if we're looking for the net force, can you see that these two vectors are at 90 degrees to each other? Hopefully, that's inspiring you to do tail to tip. So let's say, for example, I do Fg21. I do that one first. Remember, you add the next one to the tip. So to the tip of that, here's Fg23. Then the resultant goes from start to finish. That's your net force of gravity on 2. Angle goes at the beginning of the unknown vector. And there's your complete force diagram. And if you were actually solving this one, you would simply find these two forces and solve the triangle. That's it. Similar. By the way, you didn't have to draw it this way. You could also, very, very quickly, have done Fg23 first, to the tip of that, FG21, and then its resultant would go from start to finish, and it would have a different angle. We'll still call it theta, but it would be a different angle than the pink theta on the other side there. Good. Either of these two diagrams is perfectly fine. Okay, we'll finish this lesson in the next part. I'll see you then.